Welcome again, everyone. I'll talk about beyond local and gradient methods in federated learning. And this is joint work with Rustem Islamov, Shun Kian, and myself. So Rustem is a fantastic intern from MIPT. He's the first author of this, and Shun is a fantastic postdoc here at KAUST. So this is the work that I'll talk about. Distributed second order methods with fast rates and compressed communication. We have a poster that has been presented a few days ago at a workshop on communication efficient distributed optimization. For those of you who want to remind yourself about the results or just want to skim through the results, feel free to go to this link and have a look at this poster. Here's the outline of what I'll be talking about. So first, I motivate very briefly the problem setting and explain the problem description. And then I'll talk about three algorithms. First, Newton. Everybody knows what Newton's method is, but still I'll describe it and explain what are the benefits and what are the issues with Newton. Then I'll talk about Newton star, Newton learn. These are two new methods that we developed in this paper. We have some more methods, but I will not talk about them apart from summarizing some of these results on a single slide. And then I'll talk about some so this is in this further results part, and then I'll talk about some experiments. And if there is time, and there might not be, I'll talk about the Diana method and friends, because the Diana is something that is related to these new methods that we develop. So briefly, motivation, and this comes back to the title of this talk, is that distributed gradient and local methods are great, but also not so great. And I want to very briefly summarize what's really going on. So of course, we're working in distributed training and distributed optimization because that's what federated learning is about. I will not remind people what this is. But let me just go very briefly over the good things about gradient methods and the bad things. So one of the good things is that there has been a very rich research effort over the last, I would say even centuries, but of course over the last decades and years, particularly on gradient methods. So they're very well understood. Of course, there's still many open problems out there, but we understand them very well. And we also know they can provably benefit from communication compression. So I'm highlighting this one important aspect of gradient methods, which is important to distributed training and federated learning, because with the compressed communication, you could get better properties. So these methods will be faster. So there are some examples: QSGD, distributed compressed gradient descent, Diana Axer, Diana Marina, and many other methods. However, the problem of all gradient methods, and this is without exception, is that the rate depends on the problem and the data, and you're not in control over the problem and the data. So the condition number is going to hit these methods, and these methods can be slow as a result if the problem or data are bad, and if the algorithm is not handling the conditioning well. So if you're not using momentum or acceleration, then you have a worse dependence on the condition number, and so on and so forth. So mini batching improves the dependence on the condition number, importance sampling improves dependence on the condition number, and so on and so forth. So there's many of these strategies in gradient methods research are aimed at reducing the dependence of these methods on the condition number. Another issue of gradient methods is that it's very hard to tune step sizes for them. And of course, there's some recent progress on adaptive step sizes. This is one of the reasons why ADAM is so popular, because it can adapt step sizes, not necessarily provably, but in practice, very efficiently, and there has been progress on Polyak step sizes and Malitsky-Mishenko step sizes, and so on and so forth. Now, local methods. They are not that well understood, but we're getting the picture already, or piecing it together. And these local methods are typically also all of them gradient type. And this is one thing that I want to criticize here, that local methods were originally proposed because they were seen as communication avoidance strategies. So you take local steps because you want to avoid communicating. And you hope that these local steps will be useful so that when you communicate eventually, you will have to communicate less often. And that's why you could take these local steps. You don't take these local steps for some other reason. However, it doesn't actually, this doesn't actually completely mirror this effect is not mirrored in theory. So for instance, for heterogeneous data setup, which is of utmost importance in federated learning, we kind of know that these local steps are not helpful. They are helpful for quadratics when you compare, let's say, to mini-batch SGD, as was shown by Woodward and co-authors in ICML 2020 paper. And they are also good if you think of federated learning as personalized federated learning. So if you just change the objective completely and decide that you don't want to train one model, you want to train personalized model for every device, then again, local steps are actually useful. And in fact, accelerated local methods would be even optimal for personalized federated learning objectives. But for classical federated learning, these local steps are not really helpful unless you're in some special cases. And when they are helpful, the effect is also limited, and there's some dependence on condition number and so on and so forth. And there are these two.
We have one question on local methods.
Right, right.
I just muted the owner, so.
Okay.
Yeah. Hi, Peter.
Yes.
So I want to ask some question regarding the local methods. So is this something different from gradient methods, how do you define this local method?
Right. So by local methods, I mean methods which do the following: that you have a finite sum that you want to minimize, and instead of, let's say, taking one gradient or SGD step on each node, on each device, and then aggregating, averaging, and repeating, you say, I'm going to take more steps. So more gradient steps or more SGD steps or more SGD with momentum steps locally. So simply run some iterative procedure, typically of gradient descent type, locally on the local data and the local loss function before you do aggregation. So this is what I mean by local methods.
So you mean like you solve a local problem at the neighborhood of the current iterate?
Doesn't have to be neighborhood. It depends on how many of these local steps you take. So if you take many local steps, then you may depart from the neighborhood of the current iterate very far. If you take few steps, you will not get very far. But typical examples are local gradient descent, local SGD, scaffold, and so on. So federated averaging is a very good example of a local method. So much of current research on federated learning is on local methods, even to the extreme effect that whenever people say we're developing a new method for federated learning, what they actually mean is that they have some method and they add local steps to the method. So local methods, local steps are almost synonymous with federated learning at present, if you are not looking at things as personalization or privacy and so on and so forth. So I admit I'm here assuming that people know what I mean by local methods. And if they do not know, then this slide is certainly confusing. But if you do know, then this is what I mean.
So this is like in the context of federated learning, like for each we have some local updates.
Exactly. Okay. That's what I mean. So I don't mean local convergence of the type that you start close to the solution. I mean local methods, these are methods which take local steps on devices before aggregation.
Okay, thanks.
Okay, good. And the last point that I wanted to make here on this slide, let me find a way how I can go back. Okay, this way. So this is the last point, these last two red lines. So these local methods, such as local gradients and so on, they also inherit these problems of gradient methods because they're typically gradient type. That their rate depends on the problem data, hard to give step sizes, and so on and so forth. So now, because of all of these issues, I'd like to propose here a different direction of research. And we're not the first ones to suggest this, but we have some new insights. How about we look at second order methods and try to develop second order methods for federated learning? What would this mean? So first of all, current second order methods, those that have been proposed, they have one of these two issues. We're not aware of any method, distributed second order method, which does not suffer at least from one of these issues. So either the communication cost is prohibitively high. So for instance, you need to communicate Hessian matrices, or you need to communicate some large objects much larger than gradients. And then these methods simply become hard to implement or not really useful for further learning or even distributed training. Or if the communication cost is not very high, then they will resemble gradient methods to the extent that their rate will depend on the problem data again. So you don't lose the dependence on the condition number, the dependence will be there, and you cannot prove that the method is of a second order type, and second order methods, from second order methods you would expect much better conditioning. But in the existing literature, you have one of these two issues. So either you have the bad conditioning at good communication cost, or you have bad communication cost and good conditioning, but not both of these. But one of the good things is typically with second order methods, you don't have to worry about step size selection, because these Hessians and so on, second order information is going to take care of that. So one of the things that we want to do here, so the central mission here, is develop a new second order type method, or this Newton type method, which is going to be distributed, communication efficient, so the cost will not be high of communicating each communication round, and the rate we want to be independent of the condition number. So we don't have to then worry about issues such as momentum or step size selection and so on and so forth. There'll be complete independence in the rate on the condition number. So one thing that we will lose is that in order to get these qualities and these properties, we will have to deal with only local convergence rate. And this word local doesn't mean the same thing as what I meant in local methods. Here I mean that you start close enough to the solution. We also have some globalization strategies, but once you globalize, this independence of the condition number property is going to disappear. So in this talk, we're not going to resolve all the issues, but we're kind of pointing towards a certain direction in which we believe the community could be moving with some enthusiasm and because of the preliminary results that we've got. So we believe there's a lot to discover there. Now, what can you get out of this? So you could get provable benefit from communication compression for second order methods, which is a new thing. You could get a rate which is independent of the conditioning of problem data. No issue with step size selection, so these methods will be automatically adaptive. And there'll be new interpretation of what local steps mean, because we'll not be taking local gradient type steps, we're doing some other type of local work, and that can be interpreted as local steps of some sort, but local steps which actually do help in reducing the number of communications. But of course, there's also something bad about this, because we didn't solve all the issues. So for instance, the good rate only will work locally. And also for the current version of the method, we really don't care about privacy. And in fact, the method is quite bad from the privacy preservation point of view. And this is one of the things we're trying to fix now. All right, so here's the problem description. We have this complicated looking problem, but let me break this down. We want to train one model, which we call X. This is a vector in d dimensions. And this vector parameterizes some statistical model represented by d features or weights in a neural network or something like this. So that's what we want to train, and it appears in these two places. We have n machines. So this is distributed setup or federated setup, so n will be large. And each machine contains m data points. So now you may wonder, why do we not allow for each machine to contain different number of data points? This is just for simplicity of notation. There's really nothing critical about this. So in the paper and this talk, I'll just assume it's the same number of data points on each machine for simplicity. And then we have these loss functions phi ij on each machine and for each data point, and we apply them to this inner product between a data point, training data point aij, and the parameters of the model. So essentially, we have a generalized linear model that we want to train. these loss functions will be well behaved. In the initial part of the talk, I just assumed that these are some smooth enough functions. At some point, I'll assume convexity as well, or strong convexity. So again, there are training data points, Aij. I means ith machine, j means jth data point. Now, not always I want to carry this complicated notation. I forgot to mention the regularizers. The regularizer is optional here for the simple method that I will describe. The Newton-Learn method, I need this regularizer to be there and lambda to be positive, but we also have a method where this regularizer is not necessary. So this is just for simplicity of this talk and of exposition. So I don't want to carry around all of this notation always because it's not that useful. So I may want to simplify at times. So this big function, I will sometimes call capital F. So we just minimize capital F. And this little function which lives on the ith node, I will call Fi sometimes. So sometimes that's enough. That's the appropriate level of detail at which to describe some of these algorithms that I'll talk about. All right, so let's start with Newton's method. I assume everybody knows what Newton's method is, and if you don't know, you'll just learn right now. So this is a very old method. As you can see, not often do you get to cite papers from the 17th century. So Newton's method, by the way, you can buy the paper where Newton's method was described by Joseph Rapson. He developed some improvement to original Newton's method, and you can actually buy the paper for 4,500 now. So it's not that cheap, but you can actually get the original. So there you go. Newton's method is this method. It's a very simple looking algorithm. You start with your current model, xk, current vector iterate, and you subtract the action of the inverse Hessian on the gradient. And you can see I'm suppressing all the complicated structure of this problem. I'm just working with the coarsest possible representation of the problem, just with this capital F. So this is all. This is Newton's method.
Question.
Sure.
Yeah, so the question is, why do you add the regularization like lambda x squared here? Is it to guarantee some type of
yeah, so we added for simplicity. So we don't need it for the main method that we have in the paper. So the lambda could be 0. But in order to describe the simplest possible method that we have, we need this regularizer. So for pedagogical reasons, we did it because it's better to explain something that is easier to explain. For that, we need the regularizer, but then we can drop it for the more complicated method. So think of it as just a crutch, which enables me to describe method very easily. But it's not something that you really need. But oftentimes, you do need regularization for statistical reasons, and I'm not getting into that. But for this algorithm, the main algorithm in the paper, we do not need it. But I'll work with it anyway.
To compute the inverse of the Hessian, you need some that positive deafness or like some invertibility of the Hessian.
Yes, I'm going to assume things about this. So first of all, I have the regularizer here, and if lambda is strictly positive, I'm already getting positive definite matrix here. And if I assume, let's say that these functions phi ij's are convex, then the Hessian of this will be positive semi-definite, so this whole thing will be invertible. Okay. So everything is going to be fine. All right, so now I'm actually using this more refined notation where I'm plugging in for the Hessian and for the gradient. So this is actually the Hessian of this smooth part of this non-regularized part, and this is the Hessian of the regularizer. This is the gradient of this part, and this is the gradient of the regularizer. So this is again just another way of writing down Newton's method. And now let's think about how this method could be naively implemented in a distributed fashion. So let's say we want to run this in a federated learning, or let's say distributed setting. What can we do? Well, first of all, this Hessian of Fi and gradient of Fi can be computed by machine I, because machine I contains function Fi, which means it contains all the data points Aij and the loss functions phi ij, which are used to define function Fi. So this is something that can only be computed by machine I. So if we want to compute this full gradient and this full Hessian, we have to communicate. Okay, so communication is necessary because of this. So let's come up with a simple example of 3 machines. On the first machine, I have the current model XK. On the second one, current model XK. Third one, current model XK. And I have function F1, F2, and F3 on these machines respectively. So now what I do, I want the server to be computing this updated model because none of these machines contain all the information to be able to do this. So machine 1 is going to be sending the Hessian of function F1 and the gradient function F1 to the server. The same thing is done by machine 2, and the same thing is done by machine 3. And now the server, the orchestrating server, will have all the information necessary to compute the Hessian and the gradient. So this is just average of these orange things, and this is average of all of these pinkish things. Plus the regularizer, this is fine because we can assume that the server also has a copy of XK, and it will always maintain it in some extra memory. So now the server will not be doing what in federated learning typically server does, which is just aggregation or averaging. Now it will actually have to solve a linear system because it has to form this matrix and inverted apply to this gradient, which equivalently means you just solve a linear system with this system matrix, and this is being the right-hand side. And this will be then the solution. So the server will do something much, much, much more involved than just simple averaging. It'll be some very type of clever averaging or a linear system solve. Good. So now this is done by the server. Let's assume the server is powerful enough so that it can do it. So now the server computes XK plus 1 and sends this updated model back to these devices, and devices store these updated models, and this process is repeated. So all of this looks very nice, except it has this huge bottleneck compared to the gradient type methods, which are used currently, and that is that one has to send these Hessians, which are really huge objects. These are D by D matrices, and if D is millions, then this is just crazy, crazy big, and D could even be billions. So D could be very, very, very large. So that's the bottleneck, and that's why people would not really implement Newton's method in a distributed fashion, or would have very hard time implementing in this naive way. So this is a very naive implementation, obviously. Okay, so we see what the issue here is, and again, we'll not assume that it's issue for device I to compute the Hessian and the gradient. We assume it's devices are powerful enough to do that. We'll assume the server is powerful enough to solve this linear system, but the bottleneck is the communication of these Hessians. Okay, so that's that. We don't want to communicate these D by D Hessians. So how to summarize this? Well, this is something that is very well known. I'm not reviewing it. I'm just stating it here. Newton's method has a huge benefit. It will have local quadratic convergence, which is independent of the condition number. So if you start close enough to the optimal solution, X star, the speed of convergence is just going to be absolutely amazing. So not only it's independent of the condition number, but it'll be quadratic. But we need to send these all these squared objects, these matrices from workers to the master, and that is just a no-no. So you don't want to do it. Good. So here is one very, very elegant and at the same time very, very ugly trick how to solve this. So it's absolutely useless in practice, but it's absolutely wonderful in theory. And it will be a crutch which will help us to design a method which is implementable in practice and has good theory as well. So let me describe it. We call this Newton star method. So this is a new type of a Newton method which we developed. We bet this must have been proposed by someone at some point, and we would actually welcome reference, but we're not aware of it. And the method works like this. Take your current model XK and subtract Hessian inverted, but the Hessian computed at the optimal point. So that's the difference. And you apply it to the gradient. Okay. So obviously you can see that this is absolutely useless method, because how can you subtract, how can you compute even the Hessian at the optimal point if you don't know the optimal point? Well, the whole idea of this whole procedure should be to find X star. So obviously you don't know X star, and that's what you want to find. So this is not even a method that you can run. But bear with me, assume that you have it. some magical fairy tells you this is the Hessian at the optimum. What if you had that information somehow without knowing the X star? Well, then you can run this method, which is a Newton type method where the Hessian never changes. What is the good thing about Hessian never changing? Well, the good thing about that is that you don't have to communicate it, or you only communicate it once. So assume you already communicated the Hessian at the optimum from the workers to the master, then you don't have to communicate, you only have to communicate the gradients. Now the server is going to perform this Newton star step because these orange values it has, and they never change. So in fact, it has to solve a linear system with a changing right-hand side, but always the same matrix. Okay, so this is the same matrix, never changing, only this right-hand side changes. And in the next iteration, again, the right-hand side changes and so on. So you can see that this method completely resolves the communication issues of Newton's method, because you just don't communicate the Hessians. Obviously, it's useless, as I mentioned, because you don't know X star. Okay, so this method has the same communication complexity per iteration as gradient descent, because you only send d-dimensional vectors, the gradients, you only aggregate them. Yes, you do more work at the server because you solve a linear system, but when you communicate back, you also communicate xk plus 1, just like what gradient descent would do. All right, so now the question is, does this lead to some idea for developing a method which would overcome this obstacle of not knowing the Hessian at X star? So what can we do? And fortunately, the answer is yes, that one can use this idea of this useless but nice method to design a new efficient method. But before that, let me describe the theory of Newton star, because I didn't say how this method behaves. And this is the theorem that we proved in the paper. This holds for every xk, so for every k, and the method will have local quadratic convergence just like Newton's method. So the speed is quadratic, local. The neighborhood will be slightly different, but it's also local quadratic convergence. And you can see that it's local quadratic because here you don't have power 2, and here you have power 2, and this is some kind of a constant, which never changes. So if xk is close enough to x star, then this will actually lead to a rate. This holds for every single xk, and because this constant is typically much larger than 1, this is not a rate from any starting point. But once you're close enough, this is small enough for this to lead to a rate. So what is x star? That's the solution. What is mu star? Now we assume that at the optimum, the average of these local Hessians is positive definite. This is not the same as assuming that the average of these Hessians is positive definite everywhere, just at the optimum. Lambda is the regularizer, so we need either the regularizer to be positive, lambda, or mu star to be positive. We don't need both to be positive. Just the sum needs to be positive so that we don't divide it by 0. This new factor is just the Lipschitz constant of the second derivative of these loss functions. And these aij's, these are just the training data points. Okay, so this Newton star method has this nice theoretical property that it has local quadratic convergence, so that is great, but it's utterly useless, as I said, and let's try to
one question on communication step.
Okay, sure.
I just unmuted.
Hello. So in your diagram, one of the diagrams where you are communicating gradient, I think you need to communicate in only once, right? So yeah, in this diagram,
right.
At least one of the machines should send a Hessian, right? Because the server has
yeah. So at the beginning you send the Hessians. All the machines have to send their own Hessian at X star to the server, and then you don't have to do that anymore.
Yeah, so, sure.
Yeah, so that has to happen once, and I kind of assuming that already happened, and then I'm looking at the further iterations.
Sure.
Yeah, so it's not true that you don't need to communicate anything, but just communicate once. But in some sense, this is a useless method anyway, because you don't know these Hessians, some kind of abstracting from it, and the method that we'll propose will not have that issue.
Sure, thank you.
Okay, so let me summarize the good things and the bad things of Newton star. So it has local query convergence independent of the condition numbers. So that's the new result. It has cheap OD worker master communication, just like gradient descent, because you only send gradients. But of course, we don't have the Hessian at the optimum, so we cannot implement it. So how can we make this method implementable? Well, we have to change the method, and we're changing it by learning the Hessian. So this is an idea that also appears in quasi-Newton type methods, but our method is not a quasi-Newton type method. It's a different type of a method. We try to learn the Hessian in a communication efficient way. So here's the idea. Let's first look at the structure of the Hessian. So in the upper right corner, you always have the problem, just to remind you of the notation, because you cannot carry this in your minds. When you take second derivative of this, this is what you get. And notice that this has a very nice structure. So assume from now on that these loss functions are convex, so that these second derivatives are non-negative. So what you have here is a conic combination of these rank 1 matrices coming from the data, plus this regularizing term. So the Hessian always looks like this. Okay, let's now revisit Newton and Newton star from this perspective. So they differ only in these colored boxes, xk and x star. The Hessians look like this. Again, they differ only in this being xk and this being the second derivative at inner product having to do with xk, and the same thing here, but with x star. So this is how these methods look like. And we can now stare at these methods for a while to get the idea that, well, maybe we should just replace these colored boxes by something different. Okay, so I will not repeat these benefits and these drawbacks. So that's the idea. We will, so this is just a reminder that in fact we solved the problem that Newton is communication inefficient by introducing the star, but we introduced this new problem that we don't know the Hessian at the optimum. So Newton learn is the method that we propose. That's the most elementary method. We have some more complicated ones. In the paper, we called it Newton learn 1, the first version. We also have Newton learn 2, and then cubic Newton learn, but I'll only describe Newton learn. And the idea is to do something like this, where this matrix HK is some sort of approximation of the Hessian that can be maintained in a communication efficient way. And this is always the gradient, just like in these previous two methods. And the Hessian approximation, we will want this to have this format, always, this structure. So it's also going to be conic combination of these rank 1 matrices coming from the training data points. But these coefficients defining the conic combination will be something else, and we will learn them. Okay, so they will not be the second order derivatives, the second derivatives at x star or xk, but they'll be just some numbers that we will maintain. And once I tell you how these coefficients change, then you know exactly what the method is, because this is the method plus a recipe for updating these coefficients hij from iteration to iteration. So you know the half of the method already. Okay, and what do we want these coefficients to satisfy? We want these coefficients to learn the second order information at x star. If we're able to choose this hij case to be always equal exactly to this, we would be running Newton star. If this hij case were equal to this but at xk, we'd be running Newton's method. So instead, we'll just relax this and we just want these coefficients to converge to this value. Another thing that we want
on the fly.
Yeah. Okay.
Hello, hi. Just a quick question. I was wondering whether this trick works also when you get like stochastic informations from like instead of the full batch gradients, like from the workers.
So not in our paper, we didn't look at that at all. And the reason is because that's not the bottleneck. For Newton's method, the gradient is OD, but Hessian is OD squared. So we need to look at the bottleneck and not what is not bottleneck. So any kind of improvement for our method here would just simply not do anything. So we didn't look at that.
Okay, thank you.
All right. So now another thing that we want, we don't want just this. So already this looks complicated, but we want something even more. We want the differences between hi k plus 1 and hik vectors, which are now these vectors. So let's take all of these coefficients hij associated with client I. So these are m-dimensional vectors because we have m data points on each client. Okay, so this is a huge vector because each client presumably has many data points. And we want the differences between these two vectors from one iteration to another to be very sparse. Why? Because if we want to communicate this HK to the master, and if these HIJs, if these differences were sparse, then we only need to communicate those differences where the difference is non-zero. So, and this is very little information to be sent over the network. And then the master, the server, can simply reconstruct the Hessian because it knows that the Hessian always looks like this, and the only difference is in these HIJs. Okay, so this is another thing on our wish list. And lastly, we also want this method to actually have some Newton type convergence properties. So in particular, we would want to have at least a local rate, which is independent of the condition number, not necessarily local quadratic rate, but if it is, it would be independent of the condition number, at least we would get strict separation from gradient time methods, which cannot possibly have that property. Okay, so this is our wish list. And here is probably the most important slide. So I told you that this is Newton Learn plus a recipe for how to update HIJ. And now I'll explain how we update HIJ. And once I explained it, the method is fully described. So this is the update. It's quite simple looking, I would say, but let me unpack this. So first of all, HIK is just this vector of all these coefficients stored on node I. And what we do is that we take the previous vector and we add to the previous vector some delta vector, so this whole thing, some update, in order to get the new vector. So what is this? This is some compressor. And the compressor satisfies these properties. So it's some randomized mapping from m-dimensional space to m-dimensional space, and it's unbiased. So on average, it maps H into H, and its second moment is bounded in this relative sense compared to the norm of the input. So this is just a standard way in which one defines an unbiased compressor, such as a sparsifier or a dithering operation, natural compression, and so on and so forth. In the literature on communication efficient gradient methods with communication compression. So that's exactly the definition taken from there. For us, the interesting example is sparsifier, because if you sparsify, then this input, which is this difference here, could be sparsified extremely so that only one entry of the sparsified vector will be non-zero and everything else will be zero. What does it mean? It means that we only update one entry of this coefficient vector in each communication round, which means we only need to send one float to the master and not all of these. So that's where the communication efficiency will come from. So compressing the updates, and this form of the update is reminiscent of a first order method Diana. So this type of an update for a first order method was first described in this paper Diana. And if I have some time, and I certainly will not, I just look at my watch, then unless you hang out and you request it, then I can talk about it. So it was introduced there. So we borrowed the idea from there, but it's the first time this idea is actually applied to some second order method. And we're learning not first order information, but second order information. So this is some step size, and the step size is entirely dependent only on the properties of the compressor. So the best step size is actually 1 over omega plus 1 over omega is this variance factor. And this plus operation is essentially just a projection onto the non-negative orthant, because we want these coefficient vectors to be always non-negative, so that we have a conic combination of these rank 1 matrices, so that this average is always a positive semi-definitive matrix. Okay, so this is the full description of the update of these coefficient vectors. And I think I'll pause here for a question or two before I move on.
I don't see any questions or raised.
So while people are thinking of questions, I'll just repeat
Okay,
again.
we got one.
Okay, okay.
Okay, please go ahead and ask.
What is the size of n in practice? The order of n?
Order of n or m? This or n?
N.
Number of machines.
Yes.
Machines, n. Well, for here in theory, it doesn't matter. It could be anything. And in practice, depends whether you're talking about federated learning or just distributed training. If you work on a supercomputer, then n could be, let's say, tens or maybe hundreds, maybe not thousands, but not more than that. And if you work in federated learning, this could be maybe thousands or tens of thousands, something like that.
Okay.
Okay, so I will move on, but okay, good.
Okay, I just unmuted.
Hi.
Hi.
Yeah, it was just. Can you describe more in details what shape can have the compression operator?
Right. So compression operator. The best way to think of this is to give you an example, because there's a rich literature on these, and there are many examples. But for us, the most interesting is a sparsifier. So this is the operator which takes the input, which is this m-dimensional vector, okay, h. It sets everything to 0 except for one entry, and that one entry is simply just multiplied by m. And that's it. So it turns a possibly completely dense vector into a vector which is completely sparse except for one random entry. And that one random entry is just scaled up so that this thing is still unbiased. So that's the example to keep in mind. You can forget about all the other examples. So the point of this is that whatever this m-dimensional vector here produced by this difference is, this compression operator will create out of it a vector which looks like a random unit basis vector multiplied by a scalar. So it's essentially complete vector full of zeros except for one entry, which means that if you multiply it by some step size, it still has that property. So you only change one entry of this vector, HIK. Only one entry. That means that you can update the Hessian, this matrix. So this matrix from a node I, so this part, you can update it simply by just sending one float to the server. And plus, if the server doesn't know these AIJs, then you also send the corresponding AIJ to the server, and then the server can compute this Hessian approximation just from that information. And this is how you make it communication efficient. Did I ask you a question?
Yes, so we have a few more. Let me unmute one by one.
Hi. So your model, your method seems to only apply to like linear models or generalized linear models.
That's true. That's true.
Generalizing to nonlinear models like neural networks?
Yes. So in the paper, we only work with generalized linear models, but we have some follow-up work which will be finished soon, where we managed to lift this assumption. So it's no longer necessary to consider generalized linear models only, but this is something that is not online yet.
Okay, thanks.
So the trick is does not just apply to generalized linear models. And in fact, I would say there's many things which can be improved and which the community can work on. And that's precisely why I'm also giving the talk, because I believe that this is a very potent research direction, and many things can be done here, and we cannot obviously do all of them. So we can only start this and do a few things, but we need the help of the community to move this research direction forward.
Could you share a bit of intuition, like how this can be generalized? What assumptions should be relaxed?
So for instance, one thing is that Anybody familiar with Newton's method knows that people don't really use Newton's method in practice, but would use quasi-Newton type methods. So that you don't even compute these Hessians, but you compute some approximation using quasi-Newton updated formulae. So for instance, that is one direction in which one can move, that these Hessians will not even be computed fully. So these Hessians, let me go back. I'm going way back, it seems, okay. So these Hessians, but at SK, they are just not computed on the devices fully, but approximated. So this is one example of an idea, but at the moment, that's not the bottleneck. More fundamental things need to be done, but once the bottlenecks get removed, the communication bottlenecks, then that will become the bottleneck, for instance, if the worker is not willing to do that much work of computing this Hessian. And there are many questions of that type. So this is one example.
Okay, thank you.
You're welcome.
Okay, another one from Laurent.
Hello, hi Peter. So,
hi.
As you said in your response to Marie, you have either to communicate all the AIJ or the server has to know all of them. So which means
so let's assume the server doesn't. Let's assume the server doesn't know. So you only communicate the vector AIJ for that J for which this parsifier is active. So you need to communicate only one float and one D vectors, which is exactly the same thing that the gradient descent would communicate. So one D-dimensional vector plus one float. So something like one D plus one dimensional vector. And in fact, that's actually also the best setting in practice. Maximum sparsification in practice is going to be the best.
Okay, so the server gets to know all the data, but it doesn't have to store them. Yeah.
Yes, exactly.
Okay. Thank you.
All right.
The last question, maybe as of now.
Okay. Oh, that's great.
Okay, so by that you can.
Hello, Peter. So basically, you're compressing the approximated Hessian error, right? Like, broad level. The term inside your CA is an approximation error of the Hessian, right? Right.
So I compute the second order information exactly on the node, but I subtract this approximation, current approximation, and I compress that. So if I didn't compress that, and if I chose step size to be 1, if I don't compress, omega is 0. So the step size, the largest possible step size is 1. So if I don't compress, this is not there at all. These HKs, these blue things will disappear, cancel out. And this HIK plus 1 is always going to be the true second order information. And this method will just become Newton method.
Right.
So this is a way of extending Newton's method. So Newton's method is a special case of it when you don't compress at all. But what I'm saying is that compressing is better than not compressing. And this will be seen in the experiments as well. And the theory will also say something about it. Okay, thank you very much. Good, so I'll move on to the theory. So this is the basic theorem, and I'll explain all of these terms here quickly. So something which I'll describe soon, there's some kind of a thing which is good to be small, and I'll describe what it is, decreases at the linear rate. And the linear rate depends on the step size and on constant 5/8. And the step size only depends on the compression parameter omega. So this rate is completely independent of the properties of the optimization problem, independent of the data, of everything. So there's no dependence on the condition number, right? The omega is independent of condition number. So this is to us a really striking property. No gradient time method can have a rate of that type. So let's look at and this rate is only local, so that's a big thing. I'll mention this later on. So only once you start close enough to the solution, because even Newton's method doesn't converge from any starting point. And this is the thing that decreases. It's a Lyapunov function, which contains two parts. So the distance between xk and the optimal solution, and some multiple of the average of all of these squared distances between the coefficients that we learn and the true coefficients at the optimum. So since all of this goes to 0, that means that these HIJs indeed converge to the optimal values that would be used by the Newton star method. Okay, if this was 0 from all the time throughout the iterative process, then we're running the Newton star method. So this method truly learns the Hessian at the optimum. So so it's something like a variance-reduced second-order method in some sense. In variance-reduced SGE type methods, they learn the gradient at the optimum, and this method learns the Hessian at the optimum. So that's one way to think of it. So that's the theory. R is just the maximum diameter of all of these data points, and so on and so forth. So I'll pause here again for a moment in case.
Yeah, we have one more question on revealing some data points AI.
Yeah, it was, yes, this is Giovanni. Yeah, it was related to the previous answer. By revealing, finally, the AIJ depends on your local data set, right? So by revealing the AIJ, correct. Okay. So this was the issue with privacy that you were mentioning at the beginning.
Exactly. I'm very thankful you're asking that. So I forgot to highlight it. So that is issue, and of course that makes the method completely useless for federated learning. So it's okay for distributed training, but not for federated learning because we revealing the data point. But this is also something which we managed to solve, but this is something unpublished.
Okay. But perhaps you could add some noise, no?
So perhaps please be on the lookout for the second paper that we'll post next month.
Okay, thanks.
Okay, any questions about this theorem? All right, so I'm happy to return to it if anybody wants to ask, but again, I will repeat that the rate of decrease is independent of the problem completely. It only depends on the properties of the compressor. This is a local rate, so you have to be close enough to the solution. This is shared property with Newton's method, so that's another problem. We do have a globalization strategy, which I don't have time to talk about and I didn't plan to talk about. And what we learn is the Hessian at the optimum, so we have a Lyapunov function that decreases. Okay, so there's some further results, which I will not go through. Essentially, I only covered these two. For Newton star and for Newton learn, I only talk about this local linear rate, not even this local superlinear rate for the distances. And I didn't talk about Max Newton. I didn't talk about the second version of Newton learn, which doesn't need this regularizer constant lambda to be positive. And I didn't talk about cubic Newton learn, which does globalization through cubic regularization. So this I will not talk about, and I want to spend at least a few moments on experiments to show you the promise of this method. So this is some sort of baby setup with L2 regularized logistic regression and with some artificial and libSVM datasets to see whether this concept works. I will just skip this. Well, maybe I will not skip it. In one of these experiments, we compared to what we believe is the best second order distributed method, Bingo. So these authors, Crane and Rustad, they kind of show that their method outperforms these previous second order methods. So we only compared to that, and we compared to first order methods also. So let's first look at the effect of compression of Newton learn. That's what I described, this first version. The second version I didn't describe. So this is these are the plots from the paper. Let me focus just on this one. What you will see that as you increase the sparsification, so R is the number of entries of these coefficient vectors which you do not zero out. So this is the maximum sparsification strategy. Here it means that 3 of these coefficients you don't zero out, everything else you zero out. And you can see that the blue line is better in terms of communicated bits than this line. And in fact, this is a general property. As you sparsify less and less, the number of communicated bits will grow. So this suggests that it's best to use the maximum possible sparsification strategy, which means you want to be as far as possible away from what Newton's method does. So that's good, and that's why in the subsequent experiments we sparsified maximally. Now let's compare with Newton. Again, we did a bunch of experiments. Let's focus on one. So here you can see that Newton's method for this problem from libSVM with this type of regularization needs 2 to the power of 31 bits to communicate from workers to master. Whereas the best of our methods, which is this Newton learner with maximum sparsification, only needs 2 to the power of 25 bits. So this is 6 orders of magnitudes improvement in powers of 2 in terms of communicated bits. So this is not 1% or 2%. This is really huge improvement in communication, and we believe that this is very promising. Let's compare again BFGS. We see something very similar. So BFGS will have 2 to the power 36 bits need to be communicated, and we only need 2 to the power 24. So again, there's what 12 degrees of magnitude in powers of 2. So that's a huge difference too. Let's compare now again some first order method. This is accelerated Diana, so it's accelerated method with communication compression. So this is somehow the state of the art first order communication efficient method for strongly convex problems. So here we see that we also outperform all of these versions of Diana, also by quite some margin, but somewhat smaller margin than Newton's method. So these first order methods are quite efficient, but it's still several orders of magnitude. Let's compare against the second order method, the best one that we know, distributed dingo. This was published in EURIPS a couple of years ago. Again, I pick one of these plots, and we see the same picture. So dingo needs 2 to the power 31 bits to communicate, and we need 2 to the power 24. So again, it's 7 or so degrees of magnitude difference in powers of 2. So that's it. I'll stop here. I have some comments on Diana and friends for those of you who are actually interested in knowing a little bit more about this mechanism and the structure of it and so on. So I guess I'll just stop, let's say, here at the main theorem. And in case there's some questions, I'll be happy to answer. Thank you very much. And while people are thinking of some questions, in case you are, one thing that I want to somehow highlight is that if you look at what this method does locally, which is this computation of these second derivatives and compression and so on, you can think of this effort as being effort which you should compare it to the effort done by local type methods, such as federated averaging. So what they do something very simplistic, where you take the local function and you take a local SGD step, local gradient type steps, such as SGD steps, and at some point you stop and then you communicate. Here we do something else. We try to actually learn the Hessian. We compute the Hessian, and that may be costly. So the effort for aimed at computing the Hessian, which is this, is just much more useful than taking these local gradient type steps, because that effort then will lead to the reduction of the number of communications. Whereas for local type methods, you don't have a provable reduction in the number of communication unless you are in one of these special cases that I described before, plus or minus epsilon. So we kind of reinvent or rethink what the local solver on these devices should be doing, because if it's doing something like that, this will actually pay off in the reduction of number of communications. Of course, I have to again mention this caveat that all of this that I talk about has to do with the local convergence only, which means convergence once you're close to the optimum.
We got a few questions.
Yeah, so with respect to that local convergence, like, does that mean if globally it still depend on the condition number, like the
yes. Globally, it depends on the condition number, but the method can be very fast still. But I don't talk about this. I didn't include plots for the cubic Newton method, but the global convergence will depend on the condition number. So second order methods are not independent of the condition number globally, but locally they are. But then you would hope that since locally this is what happens, then something very nice will also happen globally. And in fact, we have some experiments which suggest it, but I'm not really including them here.
Okay, thanks.
So the next question by Marie. I just unmuted it.
Hi, so thanks for your talk, and I just was wondering if you have some insights on how it is possible to adapt this method for federated learning.
Right, it is, and that is exactly why I'm including this talk in the Flow seminar. But it's effort that would need to be exerted by the community to go there. So we are writing the second paper, which already doesn't have some of these deficiencies that this method does when thought of as a method that will be applied for federated learning. So for instance, one thing that it does, it will not reveal this training data information AIJ. And it will do a few more things which are federated learning friendly, which probably is best if I don't disclose, but once the paper is out, you will see. So we're completely confident that this is useful and will be useful in federated learning, but this first paper simply doesn't go as far as creating useful software that we can use now. It's just the first step. Because as I mentioned, to the best of my knowledge, is the first second order type method which can probably benefit from communication compression and has a very low communication cost per iteration. So it's a new template for how to design algorithms, I would say. And now we really need help of the community to help us push this forward into something practical.
Okay, thanks.
Peter, thank you for the talk. Can you comment why Newton Learn is better than Dingo? And also Dingo, does it has also this local independence of condition number?
No, it doesn't. So Dingo depends, the rate will depend on the condition number. So it's a complicated method. It's not easy for me to describe. But in experiments, it was best when compared to the previous distributed second order type methods before our work. So I do not really want to describe Dingo because, as I said, it's complicated. But it has good properties in terms of communication per communication round. But the theoretical rate will not be independent of the condition number, as far as I remember. Yeah, unfortunately, I can't tell you more because it's not an easy method to describe. So Mike Rabat was asking something, I noticed.
Yeah,
hey,
hi
Mike,
Peter. Thanks for the great talk. Well, thanks. Thanks for the great talk as always. Yeah. I had a question related to the experiments, thinking about Newton Learn, not directly in the context of federated learning, but just more generally as a distributed optimization method.
Sure.
So you were showing the number of bits that need to be communicated.
That's
and
right.
well, how performance changes as a function of number of bits communicated. So how do these numbers like 2 to the 24 compare to the number of bits needed to represent the data set? I'm thinking of an alternative solution as being just having each node send its data to the server, and then the server can perform Newton's method directly there.
I don't know. So you got to be there. I have no idea. We need to go there and look at this. Okay. Now, we would not want this to be possible. So if you can send the data to the server and the server just does all of this, then obviously you don't need to communicate. So kind of assuming things where we say communication is necessary for this reason that there's way too many data points for the server maybe to remember them all, but the server is still powerful enough to be solving these linear systems. So this is some sort of a setup which needs to be respected. But of course, for failure learning, you don't want the server to know the data. But this is not what you're asking. I don't know the answer to the question. It's something that I'll be happy to look at.
Thanks, Peter, for the wonderful talk. I learned a lot. I'm attending this first seminar from me. Can you go back to this? Can you go back to the slide which you had before the experiments, the take-home slide?
So which one?
I think that was
so
one HI update. I think this was a slide which only had an HI update. Maybe before this.
Right, this one.
No? Yeah, sort of. Right. So can you put all this in perspective of what the final algorithm or workflow looks like for each worker and communication? Because as far as I can understand, there's an X update, which is the global model update, which is happening at the server. And this HI update is happening locally on each client.
Right. So I should have included one more slide. I understand exactly what you're asking. So let me put it this way. So this is what the server does, right?
Mm-hmm.
Just like for Newton or Newton star. But in order for server to be able to do this, the server needs to know this HK matrix.
Right.
In order for the server to know the HK matrix, it needs to know these Hij coefficients, so it needs to be able to compute this somehow. And the way we do this is that we only send to server. So the server starts with some H0, which also the workers start with. Okay, so let's say these coefficients are set to some value, okay, at the beginning. And then we only send the deltas to these H's. So the ith node only sends deltas to Hij only for a single J. So only one of these, so essentially there's a rank 1 update to this part for each worker. So each worker sends a rank 1 update to the master, and the rank 1 update is only sent by one float and one vector. And then the master can compute one of these things and add it to its own HK. And this is done for every single I. So what the server does, it has its previous HK and just takes from node I one float, Hij for one particular J, and the Aij vector for the same J, creates the rank 1 matrix and adds it to its own HK. And this it does it for every single node. So it adds n rank 1 matrices to this HK. So somehow this can be done by the server just from this OD vector communicated by each client to the server. Yeah, so I didn't write it explicitly, but that's what's happening.
So basically, each client is basically sending HI, right? And AI and Aij.
Only update to to this HI vector. So if you put all of these J's together into one n-dimensional vector, that's n-dimensional vector, and only one of these elements of that vector are updated. And so only that update is sent. And that update is essentially this compressed difference. So this is what we send to the master, to the server. And that's essentially just one entry, one float. And the server can then multiply by this step size and do this projection to compute this HIK plus 1. And then it can compute this HK matrix.
But isn't it happening every iteration K? That means you have to send.
That happens at every iteration, yes.
Oh, so every iteration you are sending HIK, but the novelty here is that not all nodes are sending all Hessians.
No, all nodes send something, but each node only sends essentially one float, and that float is this compressed difference, okay?
I see.
And the corresponding Aij vector, one vector.
Right.
And that's enough. That information is enough for the master to be able to compute this left-hand side. And once the master computes this left-hand side for every I, it can compute the HK+1 matrix, and it can do the thing that it can do this thing.
I see. I see. All right. Thank you so much.
You're welcome. Okay, so maybe we can unmute everybody now in case anybody has questions they could ask. And if somebody really wants me to go through these 3 slides that I have on Diana, then let me know, shout, and I can do that. But I'd like to thank everybody. Feel free to log off, but I'll stick around in case there's more Q&A. Thank you very much for attending. Mary, did you manage to unmute everybody or allow
so
unmute themselves?
Yes, so they can unmute themselves if they wish to.
Right, so now you can unmute yourselves and could say anything that you wish. Something civil, please. So it seems like nobody wants me to go through these extra slides. I'll include them there anyway in case you're interested. So let me give you a 5-second version of it. The 5-second version of this is that this is the history of this Diana method for first order methods. There was this method, then this paper, then this paper, then this, then this, then this, and so on and so forth until this one. And if I was going through this without speeding like I just did, then I would explain what the purpose of each of these papers was. But this is the original Diana paper where this compression of these gradient differences was first proposed. And here it was first proposed in a single node setup. So those of you who are interested in these kinds of things, you could just go through these papers and you'll have better understanding of what's going on. Okay, good. So it doesn't seem anybody's any questions. Thank you very much. And hopefully see many of you next week.
Yeah, thank you.
Bye-bye.
Peter, just like final comments if you have time.
Sure. So I'm happy to hang around, yeah.
So what are your thoughts on, like here I understand that you're keeping data, you're sending at least one data point, right?
Right.
And I believe you're working on the privacy aspect in your next paper as well. So I just wanted to like ask you about this landscape that now that you are one of the experts in federated learning. So what are your thoughts on, like, if you have data locally on each client, and I know there are like sketching techniques or course set techniques to summarize the data so that you do not reveal a lot about it, right? And then you send the summarized data to the master to perform any update on one client rather than bringing the model to the clients. You're saying, oh, I'll send the data, but not the actual data, but the summarized data, and let the master handle the updates. So what are the challenges or problems in that technique compared to this one? Like, why isn't it a federated learning in a popular way?
So I do not know why. So I haven't seen some works where in this level of generality of just training anything, let's say non-convex models and so on, you could meaningfully do something like that. If one can do something like this with privacy guarantees, so that something, some core set or something is sent without this revealing privacy, that would be very interesting. But I have not seen something like that going on.
I see. Okay.
So of course there are some approaches which somehow resemble this, but it's not about core set. It's about just adding noise to everything and so on. But then you lose a lot of in performance. So I myself have not been thinking of these type of approaches. So I know some results in this area of core sets, etc., but not in connection with distributed training machine learning models.
Right, because in that way, then you're not willing to learn any private model, but because the entire idea behind federating setting might be that we don't want to transfer the big data across the network and make it a bottleneck,
yes.
Right? So
yeah, that's one thing, but the other thing is also you don't want actually anybody to really have access to the original data because of privacy concerns. So even if you could, but these networks, communication networks, are typically slow, and you don't want to be sending much back and forth. So that's a secondary consideration. So if you could somehow send something which is not the data and still get a meaningful result out of training on the master, that'd be interesting.
I see.
I don't know what that would be though.
Yeah, because I had tried to work there. It's under ICML submission right now, but I'm not sure how to get your thoughts on that, because I'm pretty sure you would be probably on the area chair of ICML, but probably, let's say if the decision comes out not in the favor of paper, probably I would want to like see your thoughts on that. Like,
well, you could always just send me private email and show me the paper, and we can.
Oh, definitely. Then that works, because I wanted to, because I was using householder transformation techniques for keyword decomposition. So in that case, if you are familiar with that, like the covariance is kind of preserved, right? If you do X equal to QR, and eventually the covariance in an original formulation is XX transpose. So you have now RR transpose as the covariance in the new formulated setup.
Well, like I can't quite follow, because I don't know what your notation actually means. But are you talking about some quadratic problems, or this is general?
Yeah, quadratic, like convex problems in that setting.
Okay.
Like to begin with, X is the data, N cross D, and if typically, like, I think this setup works if D is smaller than N. Then if you do a local QR decomposition.
Okay, but isn't what you're doing already something? Because once you have convex quadratics, then and you start talking about covariances, then you're almost talking about Hessians of these local functions. And once you do QR or something like this, you do something like compression of the Hessian. So you already do something similar to what we're trying to do here, if you think about it, right? So there's some similarity there.
Yeah.
So maybe that should be explored, that similarity.
Can you comment on that again? I didn't catch the last.
So maybe that similarity should be explored, because as far as I understand what you said, there is some similarity with this.
I see.
So these covariances that are probably related to Hessians of these local functions, right? Once you do decomposition, it's some sort of a compression of the Hessian.
Right. It's basically a sketch. It's a QR sketch. Of
right. So it's linear compression. So sketch is a type of compression.
Right.
Because this compression that we consider could also be sketch in some sense. You could just have a random matrix and multiply by a random matrix. So so it seems there is some relations here. So I think we can definitely have a chat.
So I'll send you the paper with private email, and probably I can then.
Okay.
So we can discuss from there. Because I've been following you on Twitter a lot these days. I liked your initiative on the new conference ideas and everything.
Thank you very much.
So I've started, I have done a lot of idea sharing on that Google Doc as well. So
that's great. That's awesome.
It would be good to connect to you as well, and then think how you look at it, that paper as well.
Great. Thanks.
Thank you so much, Pete. Thank you. Take care.
Thank you.
And by the way, I'm JD. I'm finishing my PhD from Texas A&M in College Station.
All right. Well, pleasure to
my pleasure.
Talk to you. All right, so I stopped sharing. Thanks, Mer, for helping with these questions. That was very helpful. As I said, I wasn't able to be digging for them on the second monitor. And thanks, everybody, for sticking around. And see you next week. Bye-bye.